Hello, everybody. Today, I want to start by talking about something that you very well may be familiar with, the idea of a batting average in baseball. If someone has 6 at bats, and in those 6 at bats, they get 3 hits, that's what we would call a batting average of 500 or 0.500. We get that by dividing the number of hits or successful at-bats from the total number of at-bats. I picked some small numbers here. Let's say sometime later, the player has 60 hits in 240 at-bats. This batting average would be 250, 0.250. What if we wanted to know how many additional hits he would need to improve his batting average to 0.280 average? Well, we could figure that out by solving the equation 60 plus x over 240 plus x equals 0.280. Now, as of right now, we don't know how to solve an equation like this, but I wanted to start by introducing an application because the types of equations we're going to see in these next few lectures that we're going to be building towards the application problems of, you might think, when am I ever going to need to do something like this? And this is a nice example of, well, just watching baseball. If you want to figure out, hey, that guy there has a 250 batting average. If he just got hits from now on, how many hits would he need to raise that batting average to 280? It's not a likely situation, but it is a situation. The reason we would add X to the top and the bottom would be because if he only had hits from now on, those hits, those successful at-bats would also be total at-bats. So we would add that number to the top and the bottom, and we would want the average, the batting average, to work out to 0.280. So now that we know what types of equations we're going to be looking at by viewing an example, let's define what we're going to be talking about. Notice it looked like we had a fraction. An expression that has a fraction in it looks like it has a numerator and a denominator, but it is a single expression. That is called a rational expression. Just like a rational number is a number that can be written like a fraction, a rational expression, notice root word ratio, also looks like a fraction. And if we use rational expressions in an equation, that is, if we start putting equal signs in there, then we have rational equations. Let's take a look at x over x minus 3. This is a rational expression because we see it's written as a fraction. It has a numerator, it has a denominator. What would be the value of this rational expression if x equaled 6? So if x equals 6, what would be the value of this rational expression? We can figure that out by plugging 6 in for x. If x is 6, then we have 6 over 6 minus 3, which is 6 over 3, which is 2. So if x is 6, this expression is 2. What about if x was negative 3? If x was negative 3, we would have negative 3 over, careful with your signs, negative 3 minus 3. This would be negative 3 over negative 6. Negative divided by negative is positive. This is positive 1/2. So if x is negative 3, this expression would have a value of positive 1/2. We found that by plugging negative 3 in for x. What about if x was 0? If x is 0, what's the value of this function? Well, notice that makes the top 0. And even though on the bottom we would have 0 minus 3, since it's 0 over a number, that means it's just 0. 0 divided by anything is 0. So 0 on the top, that's okay to have. It gives us 0. What about, let's do this one final time with this same expression, x over x minus 3. What if x was positive 3? Well, that would give us 3 over 3 minus 3, which would be 3 over 0. Uh-oh. 0 on the bottom of the fraction, dividing by 0. That's undefined. Which means if x is 3, we don't have a value for this expression. So 0 on the top, that's okay. That just gives us 0. 0 on the bottom makes it undefined. These numbers that are going to cause our rational expressions to be undefined are going to be called restricted values. So what are restricted values? Restricted values are values for x that cause our expression overall to be undefined. What causes things to be undefined? Well, denominators being 0, the bottom of a fraction being 0, divided by 0. So the way we can find our restricted values is by taking the denominator of the rational function, in this case, x minus 3, and let's set it equal to 0. Add 3 to both sides, we get x equals positive 3. So x equals positive 3 is a restricted value because it causes overall the bottom, the denominator, to be equal to 0. Let's find some more restricted values. if we had x minus 7 over 3x plus 5, what would be the restricted value? Well, we find these by taking the denominator, 3x plus 5, and setting it equal to 0. Subtracting 5 from both sides, 3x equals negative 5. Dividing both sides by 3, x equals negative 5/3. So x equals negative 5/3 is the restricted value. Plugging in negative 5/3 for x causes us to have 0 on the denominator. What would be any restricted values of negative 5 over 3x squared plus 6x? What would be the restricted values? Well, it would be what we get when we take the bottom, 3x squared plus 6x, and we set it equal to 0. We have a quadratic. What do? Everything on one side, 0 on the other, factor, and solve. Everything is on one side. We do have 0 on the other. So let's factor. 3x squared and 6x. We have a common factor of 3x. Our leftover piece would be x plus 2. 3x times x is 3x squared. 3x times positive 2 is positive 6x. Factor and solve, because we could use the 0 factor property. Either 3x equals 0 or x plus 2 equals 0. Divide both sides by 3, we get x equals 0. Subtract 2 from both sides, we get x equals negative 2. These are both the restricted values of this expression. They are the values that will cause us to have 0 in the denominator. Let's do restricted values again. Let's find the restricted values for the expression 3x over x squared minus 7x plus 6. So restricted values are what we get when we set the bottom equal to 0. It's a quadratic. Everything on one side, 0 on the other. Factor and solve. We would need the two numbers that multiply to positive 6 and add to negative 7. These two numbers would be that multiply to positive 6 and add to negative 7. That's going to be negative 6 and negative 1. Those aren't the restricted values. Those are the numbers we're using to factor. Go ahead and take each factor and set it equal to 0. X minus 6 equals 0. X minus 1 equals 0. Add 6 to both sides, we get x equals 6. Add 1 to both sides, we get x equals 1. Positive 6 and positive 1 are the restricted values. Positive 6 and positive 1 are the numbers that if we plug them in for x, they will give us 0 on the bottom, which makes it undefined. Restricted values again. We have a plus 10 over a squared minus 25. What are the restricted values? Well, the restricted values are what we get when we set the bottom equal to 0. Now, 2 ways to solve this that we know about. We could factor and solve. As a difference of squares, this would be a plus 5 times a minus 5. Set both of those equal to 0 and solve to get a equals negative 5 and a equals positive 5 as the restricted values. But you could also use the square root property here because we just have a square term and a constant. We can easily get the square on one side and everything else on the other, so we can do square roots of both sides. Be careful if you do it this way that you remember a plus or minus 5. A equals positive 5 or negative 5. When we take square roots of both sides of an equation, we have to remember the plus or minus. So one way or another, we would set the bottom equal to 0 and solve to get a equals positive 5 and a equals negative 5 as the restricted values for this expression. It's about time that something fun happened, relatively speaking. 2x cubed plus 5 over x squared plus 9. Well, to find the restricted values, which is what we are still doing, we would take the bottom, we would set it equal to 0, and we would solve. There is no way to factor a sum of squares. If this was x squared minus 9, we would do x plus 3 times x minus 3. We would be on our way. But we can't factor a sum of squares. A sum of squares is prime. If we went and used the square root method, we would get x squared equals negative 9. And we know now with complex numbers, x would be plus or minus 3i, the square root of a negative number. But when we're talking about restricted values, we're talking real number system only. So while we know that with complex numbers, we can do I, when we're talking about the things that we can and can't have for x, those are real numbers only. And in the real number system, we cannot take the square root of a negative number. That means we have no solution. That means we have no restricted values. There are no values of x that would cause this to be undefined. And let's look at this, because that does make sense. When we square something, it's going to be positive. The smallest number we can have is 0, because if we plugged negatives in, a negative squared is a positive. So 0 squared would be 0. That's the smallest we could have for x squared. But then we add 9. So the smallest that the bottom of this fraction could possibly be is 9. It can never be 0. So there's no restricted values. There's nothing that can make the bottom 0. And when we try to set it equal to 0 and solve, we would get no solution because of that, because it's not possible to have 0 on the bottom here. So when I teach fractions, I make a point of saying, hey, it's real important that you learn these rules for adding fractions, for subtracting fractions, for multiplying them, for dividing them, for reducing them. Because down the line, you're going to have to know how to do all those things with rational expressions instead of just the fraction 2/3 fractions that have expressions on the top and expressions on the bottom. And here we are. So our path is going to be a lot like the path for learning how to work with fractions. We introduce numerator and denominator. With rational expressions, the denominator can't be 0. That's a little more interesting in expression land, because in number land, dividing by 0 can only look like a 0 on the bottom. But we started working with these expressions. So instead of just saying, hey, watch out for a 0 on the bottom, this turned into a whole discussion about restricted values, which give us restricted values give us 0 on the bottom. So what did we learn about with fractions next? Well, after we introduce what a fraction is, we start talking about reducing fractions. So just like we simplify fractions, let's work on simplifying rational expressions. Let's say we had two x cubed plus 12x squared plus 16x all over 6x plus 24. Well, the thing you absolutely cannot do is go, oh, 2 over 6, that's 1/3. You can't go, oh, 12 over 6, that's 2 over 1. You can't just pick something from the top and pick something from the bottom and cancel them away. Not when it's written like this. If we had the fraction 4/8, it's because of the fact that this is 4 times 1 over 4 times 2 that we can cancel the 4s and be left with 1/2. It's because when it's all written as multiplication, that's the key. When it's all written as multiplication, something times something times something times something all the way across. Then we can cancel common factors. There's no such thing as canceling common terms. It's common factors. That same thing's at play here. So we just can't pick this term and decide, hey, let's cancel those. It doesn't work that way. In fact, if it helps you to think about, this is like having 2x cubed over 6x plus 24 plus 12x squared over 6x plus 24 plus 16x over 6x plus 24. How do we add three fractions with a common denominator? Well, when it's the same thing on the bottom, we leave it on the bottom and then we add across the top. So that's why we can't just make this 6 go away if we cancel it with the 12, because that 6 still exists as a part of the front and the back. Only by writing everything as multiplication, only by writing everything as factors can we reduce. And that's why we just learned how to factor. So let's factor the top. Let's factor the bottom. What's the first step in factoring anything? That's right. See if we can factor out a greatest common factor. On the bottom, 6x and 24, we can factor out a 6. We're left with x plus 4. On the top, we can factor out 2x. And what are we left with? We're left with x squared, because 2x times x squared is 2x cubed. 2x times positive 6x would be positive 12x squared. And 2x times positive 8 would be positive 16x. And this factors further. So if we wanted to factor x squared plus 6x plus 8, x and x, we would need numbers that multiply to positive 8 and add to positive 6. Those numbers are positive 4 and positive 2. So completely factored, the numerator here would be 2x times x plus 4 times x plus 2. The denominator would be 6 times x plus 4. Now, we're not done. But before we take the next step, I want to take a moment and talk about the restricted values. In a problem that has a bunch of factoring like this, since the common thing we do to find the restricted values, we set the bottom equal to 0 and solve, it becomes much easier and something that we're likely going to do anyway to make sure the bottom is completely factored. And then we can find our restricted values. So along the way here, we ended up factoring the bottom completely. We got 6 times x plus 4. And if we set that equal to 0, we get 6 equals 0. We get x plus 4 equals 0. 6 plus 0 is absolute nonsense. X plus 4 equals 0. We subtract 4 from both sides. We get x equals -4. So x equals -4 is our restricted value. Why did I just pause the problem, which by the way was write this in simplest form? Well, it's because that factor that we got the -4 from, that x plus 4 that we set equal to 0, that we must set equal to 0 to find out that it's a restricted value, that factor just canceled away. So we got to find it here at the beginning of the problem, because by the end of the problem, that information might not be there anymore. We could also reduce now the 2 over the 6 to 1/3. 1/3. And 1 times x is just x. So what we have here is x times x plus 2 all over 3. This and this are the same. But actually, I'm going to uncircle this for a second. There are some restricted values, like this one, that we must name. So this here, the original problem, the original expression, is equal to this, provided that x is not -4. And we explicitly say that because it came from a factor that canceled. Could we look at, let me erase everything here except the original problem and the answer. Can we look at this and know, without it being said, that x can't equal -4? If all we saw was the x times the x plus 2 over 3, we would take the bottom, we would set it equal to 0, and then we would solve to find restricted values. 3 equals 0 is nonsense. So we would come away thinking there are no restricted values. And if we plug -4 in to x times x plus 2 all over 3, we get -4 times -2 all over 3, positive 8/3. We get an answer. But if we plug -4 into the original version, 6 times -4 is -24. -24 plus 24 is a big ol' honkin' 0. -4 makes this thing have a 0 on the bottom. -4 is undefined. When we reduce this expression to x times x plus 2 all over 3, since that information is not visibly explicit to us anymore, we have to say, hey, don't make x -4. That value you get, that positive 8/3, that's a lie. You don't get 8/3 if you plug it into the original. And what's the whole deal about reducing fractions? 4/8 reduces to 1/2. They are equivalent. In every sense of the word, 4/8 equals 1/2. So you can't say this equals that except for that one time where if you plug it in here, it's undefined, and you plug it in here, it's positive 8/3. We can't have any of that. So we say x can't equal -4. If you're confused, I promise you I didn't do so much there. I just talked a lot. We're going to do another example right now to drive this point home, show, hey, if I know how to find restricted values, if I know how to factor, I can reduce rational expressions. In fact, when you think about it, what we're doing isn't really all that new. You know how to reduce fractions, you know how to factor. Now we're factoring to reduce fractions. That's all. Let's reduce x squared plus 3x minus 28 all over 2x plus 14. 2x plus 14. Well, if I factor the top and I factor the bottom I can factor out a 2. I'm left with x plus 7. On the top, I need two numbers because this is going to be an x times an x. I need two numbers that multiply to -28 and add to +3. These would be +7 and -4. They multiply to -28. They add to +3. So in goes a +7. In goes a -4. Now I've completely factored the top. I've completely factored the bottom. Before I cancel, I look for my restricted values. I take my factored form on the bottom. 2 times x plus 7. I set that equal to 0. I get 2 equals 0. I get x plus 7 equals 0. What is 2 equals 0? Nonsense. That's right, it's nonsense. Here, subtract 7 from both sides. X equals -7. This is my restricted value. It's going to be important that I found that because it's coming from the x plus 7 factor, which is gone. So this completely reduces to x minus 4 over 2. And since we can't see that x plus 7 factor on the bottom anymore, we have to say, hey, x cannot equal -7. Make sure here, since it's a restricted value, we're saying x cannot equal that you're using the not equal sign. In fact, if you want to go through and put it there, you can. I don't do that though, because I don't want to accidentally get confused. When I come over here, I go, hey, 2 equals 0. That's nonsense. If that said 2 doesn't equal 0, I might forget to say that's nonsense. So I find my restricted values. I just remember that when I write it here, we have a not equal sign. So remember when we worked on the exponent rules. Our next example is not a new problem. 2/8 is 1/4. We can keep it all together, play how many more where. For the x's, how many more where? We have x to the 4th on the bottom, squared on top. That's 2 more on the bottom. For the y's, how many more where? I got 5 more on top. That's a y to the 5th on top. 1 times y to the 5th is just y to the 5th. 4x squared on the bottom. Is there any restriction we should name here? Well, since originally we had a factor of y on the bottom, that means that y can't be 0. We can still see that x shouldn't be 0, but we can't see that y isn't 0 anymore. So I'm going to go ahead and say y can't be 0. And I'm going to make that part of the answer. The book mentions it. Doesn't make a point of putting it with the final answer here. I would. Again, simply because here in the original version of the problem, we can clearly see y shouldn't be 0. That would cause a big issue. So y being 0 needs to cause that same issue at the end. Since it doesn't, we go ahead and add that in. So I had played the how many more where game, but again, we can have gone 2/8. That's 1/4. And then x to the top minus bottom, 2 minus 4. Y to the top minus bottom, 8 minus 3. That's 1/4 x to the negative 2, y to the positive 5th. Negative exponents go on the bottom, so to the bottom with the 4. And the y to the 5th will come up top. It's times the 1. And again, you can say y cannot be 0 there. Next up, t cubed plus 8 over t squared plus 4t plus 4. Let's go ahead and factor the top, factor the bottom. On top, this is a sum of cubes. We can use that SOAP formula. For the sum, for the plus, same as the plus, opposite of the plus, always plus. Our two things that are being cubed here, this is t cubed plus 2 cubed. So t and 2. T squared, multiply them together, 2t, square the 2, 2 squared is 4. Square the first, multiply them together, square the second. On the bottom, this, if you're following the, I don't want to call them rules, but if you're following the step-by-step how to factor anything, we've got factor out a greatest common factor. We don't have that. Ask yourself, is it 2, 3, or 4 terms? On the top, it was 2 terms. It was a sum of cubes. We factored appropriately. On the bottom, it's 3 terms. You should, at that point, ask yourself, is it a perfect square trinomial? In this case, it turns out, why, yes, it is. This is what we get when we square t. This is what we get when we square 2. And 2 times 2t is 4t. It was a plus here, so this is t plus 2 quantity squared. But it's okay if you didn't ask yourself if that's a perfect square trinomial, if you didn't factor it using the special formula. You would just be looking for 2 numbers that multiply to +4 and add to +4. Those numbers would be +2 and +2. T plus 2 times itself is t plus 2 squared. Since t plus 2 times itself is t plus 2 squared, for the sake of the visual, let me write it that way. The visual being, I'm going to cancel that. So we're left with t squared minus 2t plus 4 over t plus 2. Now, it is only because of the fact that we still have that t plus 2 left over that we didn't have to say, and by the way, t can't be -2. Because, yeah, our restricted values is actually only one restricted value, a t minus 2 that we get twice. So even though one of those got canceled away, we were still left with the other one. So we can still look at our answer and see, hey, t can't be -2. And because we still see that information, we don't have to say it. And I said, for the visual, I'd show it that way. But if we had a t plus 2 squared on the bottom and a t plus 2 on the top, canceling one of them on top is canceling one of the factors on the bottom. Just like x over x squared would end up 1 over x. How many more where? One more on the bottom. T plus 2 over t plus 2 squared. When the t plus 2's go, it still leaves us with one factor on the bottom. So lots of ways to write the factored step, the cancellation there. But in the end, you'll have t squared minus 2t plus 4 over t plus 2, no restriction needing to be written. Let's do another just like this. Let's take a look at p cubed minus 27 over p squared minus 6p plus 9. When I said just like this, I wasn't kidding. The bottom is a perfect square trinomial. This is p minus 3 squared, actually. This is what we get when we square p. This is what we get when we square 3. This is what we get when we multiply them together and double. 3p times 2 is 6p. That's what makes it a perfect square trinomial. That's why we can make it p and 3 squared, and the minus is why it's a minus here. On top, p cubed minus 27 is a difference of cubes. The two things being cubed are p and 3. Set up our SOAP formula. We're starting with subtracting 2 cubes. So same as the minus, opposite of the minus, always plus. P and 3, p squared, 3p, 3 squared. 3 squared is 9. The factor of p minus 3 on top cancels with one of the factors of p minus 3 on the bottom. P squared plus 3p plus 9 over p minus 3. It's as simplified as we can take it. We don't need to explicitly say p can't be 3 because we can still see that information. Since we can still see a p minus 3 factor on the bottom, that tells us that p can't be 3. We don't write it again.